Welcome to my classroom. In this fuel cells and batteries course, in past 6 lectures, we have seen about the history of fuel cells and batteries, and we have seen the principles of fuel cells, what is the chemistry behind it, and we have introduced about classification of fuel cells, and in that we have seen what is a PEM fuel cell, what is alkaline fuel cell, and what is phosphoric acid fuel cell. And in this lecture number 7, we will discuss about the thermodynamics of fuel cells. Okay, so at the end, we will have an expression for efficiency of a fuel cell. And in the next lecture, we will be solving few numericals also. So in lecture number 7 and 8, we are going to discuss about thermodynamics and efficiency of fuel cell. So getting into this thermodynamics and efficiency of fuel cells, before doing that, let us get back to what is a fuel cell. If we consider the fuel cell, what is happening in the fuel cell as a process, so we are having some input and there are outputs. Okay. So if you consider the inputs, hydrogen and oxygen are the inputs, and output are, there are 3 types of output. One is electrical energy, heat, and then water is the product, right? So considering the energy of the system, we can say the Gibbs free energy change. So for that, if you look at this electrical power and energy output of the system, it is easy to calculate them because we know the formula for power is calculated by V into I, and energy is power into time. So VIT gives us the electrical energy output. Okay, but if you look at this chemical energy of the input of hydrogen and oxygen or the output of water and other heat, so to measure that the chemical energy of this input and output is a little more difficult to define, because it is a change in the Gibbs free energy that we must consider in this case. Or if you want to say in precision, we can say it is the Gibbs free energy of formation. That is the energy of formation, because we use the convention of comparison to pure elements in their standard states. What is the heat of formation of pure elements? It is 0, right? So for anything which is formed out of it, we can get the energy of formation of them, right? So we know the energy of standard energy of formation of pure element is 0. And with this only, we will come to know the energy available to do the external work. Okay. So in this case of a fuel cell system, this external work is, what is the external work it is doing? The electrons are flowing through the external circuit. So that is the external work it is being done. Okay. So this external work is pushing the electrons to the external circuit and past whatever impedances we could put in their way. Okay, and work done by the changes in volume and temperature between the input and output, it is not harnessed by the fuel cell. Okay, but however it is possible in a case of turbine hybrid systems. Okay, we know that fuel cell is an electrochemical device that converts chemical energy of the fuel and oxidant. What is oxidant here? Air or oxygen, directly and reversibly into electrical energy. But they are not a better or improved heat engine. They are fundamentally different from your heat engines. Okay, so hydrogen and oxygen are used to illustrate the thermodynamics of the fuel cell. However, other reactants are also used, right? Other fuels can be also used, like methanol, other can be used as a fuel. However, to define these thermodynamics or understand this thermodynamics, we will assume that hydrogen and oxygen are the reactants used in the system. Okay, so as I told you, the heat of standard heat of formation of these pure elements of oxygen and hydrogen is 0, which will be a useful result while dealing with the hydrogen oxygen fuel cell. That is the reason we are starting with hydrogen and oxygen. Okay, so what is that Gibbs free energy of formation is symbol represented by, it is represented by the symbol delta GF. Okay, delta GF refers to the difference in Gibbs free energy of formation between the input and outputs, and therefore a specific measure of energy released by the reaction. So by any reaction, if you want to write what is delta GF, we can write it is the Gibbs free energy of formation of the products minus Gibbs free energy of formation of the reactant. So this minus this gives us the change in Gibbs free energy of the reaction. Okay, and we write it per mole. Okay, usually we consider this quantity to be per mole of the substance, because we write A plus B, we say 1 mole of A plus 1 mole of B, right? In our case, it is H2 plus of O2. So we can say 1 mole of hydrogen reacts with 0.5 moles of oxygen. So that is the reactant ratio which is being used. Okay, so that way we try to refer it with respect to a mole per mole of a chemical. Okay, so let us find the chemical energy released during a nominal fuel cell reaction. Okay, so for that we should know what is the reaction that is taking place. We have seen that we have a reaction taking place at the anode. We have a reaction taking place at the anode. What is that? It is HOR. That is hydrogen oxidation reaction. So the reaction taking place at the anode is the simple hydrogen oxidation reaction. And it involves multiple steps. Okay, we will simply say that the hydrogen evolution reaction, hydrogen oxidation reaction, but it may involve multiple steps, which we will discuss later. Okay. And there are reactions taking place at the cathode. We have reactions taking place at the cathode. What is that ORR reaction? What is that ORR? It is oxygen reduction reaction. Remember, ORR, understanding the ORR reaction is still a very good research area, study, okay, research area of study. Okay. Understanding this ORR reaction because it varies with different metal surfaces or catalyst used. Different cathode surface, we have different type of mechanism taking place. So that's a very good research area for studying that one. Okay. Now, and this, as I told you, is why it is an interesting research area because it is more complex. This reaction taking place here, it is much more complex to explain. Okay, and it involves a dozen of potential reaction steps. Why it is complex? It involves at least 12 steps. So a dozen of potential reaction steps. Remember, it is like multiple step reaction, single step reaction, multiple step reactions, we know. So these both are multiple step reactions. So in comparison, hydrogen oxidation reaction, HOR is also a multiple step reaction, but ORR reaction is much more complex reactions. Okay, and if you consider the acid electrolytes, if you consider for acid electrolytes, like in phosphoric acid fuel cells, for this one, H plus ions will be transferring from anode side to cathode side. We know that the reaction taking place is H2 will give H plus 2 electrons, right? So we want that. So what happens is this H plus ions will be passing from the anode side to cathode side through the acid electrolytes. So H plus ions will be passing from the anode side to cathode side through the acid electrolytes. Okay. So what is the ORR reaction taking place? ORR reaction taking place is 0.5 oxygen plus these two H plus ions which will coming to this side will and this through external circuit, these electrons also will come to the cathode side. So all of them together forming water. Okay. So this is the reaction taking place at the cathode when for even these phosphoric acid fuel cells. Okay. That is for acid electrolytes. For acid electrolytes, this is the reaction taking place. Okay. Whereas for alkaline electrolytes, negative ions from the cathode to anode will be moving. Okay. That is, we say it is cations. Anions will be moving from negative electrode to, or you can say from this, for alkaline thing, negative ions will be moving from cathode to anode. So here anode to cathode is the movement taking place. Here negative ions are moving from cathode side to anode side. We have already discussed what is the ions that is moving for each type of fuel cell in our previous lecture. You can refer to that. So there is movement of negatively charged ions from the cathode side to anode side. Okay. So for example, you can say for alkaline electrolytes, the what is the HOR is, this reaction will be like H2 plus 2OH minus ions will form 2H2O plus 2 electrons, and these electrons will be moving through the external circuit. Okay, so this is what takes place at the anode. Okay, so anode we have HOR reaction. So remember in previous case also we have anode reaction, but the reaction was like this: H2 becoming H plus and electrons. Okay, whereas if it is an alkaline electrolyte, from the cathode side we have OH minus ions coming to the left hand side, that is to the anode side or the fuel side. Therefore the reaction taking place is water is formed in the anode side for alkaline electrolytes. So what is the reaction taking place at the cathode side? Again it is ORR reaction only taking place. So how it takes place is O2 plus 2H2O plus 4 electrons will form 4 OH minus ions. So that only moving across the electrolyte. Okay, so for the alkaline electrolytes, what is the reaction taking place at the anode and cathode? For acid electrolytes, what is the reaction taking place at the anode and cathode? Okay, so this is the reaction taking place at the anode. This is the reaction taking place at the cathode. Okay, so you should be able to write for acid electrolytes, write neatly in your notebook. What is the reaction taking place at the cathode? What is the reaction taking place at the anode? Similarly, for alkaline electrolyte, what is the reaction taking place at the anode and what is the reaction taking place at the cathode? Okay. And if you observe one thing, what we can observe here is conservation of charge is taking place. Conservation of charge. What is the concept of conservation of charge? Anodic and cathodic reactions are independent. Remember, they are independent reactions. What is taking place at anode is independent of what is the reaction taking place at the cathode, but they are interlinked by one factor. What is that? They are coupled by one factor. What is that? That is that necessity to balance the overall reaction. Overall reaction is balanced. Whatever is the number of steps involved in the anode reaction, whatever is the number of steps involved in the cathode reaction, so the overall reaction is balanced always. So when you say balance, what is that meaning? All the electrons produced in hydrogen oxidation reaction at anode is to be consumed by ORR reaction at the cathode side, because these electrons will be passing through the external circuit. Okay, and remember this electron is in this direction, means then the current is in opposite direction to the electron transfer, right? So that we know about the current. Okay, what about current? We know that current is the flow of charged species. Current is the flow of charged species through the electrolyte. We know that H plus ions or OH minus ions will be passing through the electrolyte in the form of ions. Okay, either it is positively charged ions or negatively charged ions, and the external circuit. Okay, so this current is passing in the opposite direction. The current is in the opposite direction to the electron flow. Okay, So it is defined as, what is current? It is defined as the flow of positive charge and is thus movement in a direction opposite to the electron flow. So that you can write it in a sentence. It is defined as the flow of positive charge and is the movement in a direction opposite to which flow? Electron flow. Okay. So this we should know. So the current is always flowing in opposite direction. It is through the electrolyte as a charged species and in the opposite direction. Okay. For both galvanic and electrolytic reactions, these electrons are conducted from anode to cathode through the external circuit and to the cathode. Okay, that we know. Okay, so these electrons are passing from the anode side to cathode side, that is hydrogen side to oxygen side through the external circuit. These electrons are flowing. Okay. Now, coming to the first law of thermodynamics, so just recalling about before getting into the derivation, we'll just recall first law of thermodynamics. So actually, Joule experiments, James Joule, actually in 1843 to 1848, James Joule performed some of the experiment on paddle wheel setup. Okay, so we consider a paddle wheel setup. So that experiment is the basis for the formation of the first law of thermodynamics. Okay, so for that what he consider is, he considered two processes. So first process is he consider a liquid in an insulated container. He consider a container and a liquid, and he consider a paddle. The paddle is like stirrer, okay, and it is insulated. In an insulated system, insulated container, he vigorously stirring of liquid was taking place using a paddle wheel. Okay, so this using a paddle wheel, he checked what is happening by stirring it with a paddle wheel in an insulated container. What is happening at a constant temperature? When you are insulated, it means that temperature is constant. Okay, so that is one process he tried, and he tried another process where the insulation is removed. Okay, so insulation is removed, and he allowed the transfer of energy, okay, in the form of heat from the liquid to the cooling water till the liquid reaches the original temperature. Okay, so that's what considered. So in the second process, the insulation is removed and transfer of energy is allowed. And transfer of energy is allowed in the form of heat from the liquid to the cooling water till the liquid reaches the original temperature. That is the second process where you have, so the some cooling setup was there. Okay, so we can say some cooling setup. So the cooling was allowed to happen so that the temperature is coming back to original state. So this way the system is restored to its original state. So what we can say is the system initially was at a temperature, then the once stirring is taking place, okay, some work is done on the system, so there is a change in temperature and it comes back to original temperature T. So that way a cyclic change is taking place in the system. So the system is restored to the original state wherein it is subjected to a cyclic change. So what is the inference from this? The work done is equal to heat removed. Work done that is the work done by this paddle wheel is equal to the amount of heat removed through these cooling waters. Okay, so we can write for a cyclic process, integral dq is equal to integral dw. So what you can say, integral over the entire cycle dq is equal to dw. So what is integral dq? This is the heat lost from the system or energy removed from the system, and integral dw is the work done on the system. Okay, so what is the sign convention? If you want to use work done on the system minus w, work done by the system we'll write plus w, heat supplied to the system we'll write q, and heat removed from the system minus q. So that is a sign convention. If you consider the system as the reference, we will write that. Okay, now so from this what we can write is, you can take it to the left hand side, you can write integral dq minus integral dw is equal to 0. And remember, it's not only applicable for reversible process, it is applicable for both reversible and irreversible processes. Okay, so we can say, what is first law of thermodynamics? Whenever a system undergoes a cyclic process, the work done on the system is equal to the energy transferred as heat from the system to the surroundings. Okay, so that's what first law of thermodynamics is, and there is a consequence of this first law. What is that? Heat interaction depends on the path followed by a system, and it is a path function, and there exists a point function called as energy, E. Okay, so what is energy? Okay, it's a macroscopic system. Any macroscopic system will possess some of the energies in the form of potential energy. Okay, so this potential energy depends upon the location and configuration. And we have kinetic energy, which again depends upon the motion, where we come and discuss about internal energy, random motions, internal structure of atoms or molecules, constituting atoms or molecules. They all define what will be the kinetic energy, right? So this energy can be written as E is equal to sum of potential energy plus kinetic energy plus internal energy. Okay, so any macroscopic system will have potential energy, kinetic energy, and internal energy. Okay, so that is if E is the energy. So what is change in this can be written as any change in this energy is equal to any change, then change in, so taking differential, change in potential energy plus change in kinetic energy plus change in internal energy. Okay, from first law of thermodynamics, what we have is change in energy is equal to, this is from first law of thermodynamics. Okay, dE is equal to dq minus dw. Okay, so we can write dE is equal to d of potential energy plus d of kinetic energy plus d of u is equal to dq minus dw. Okay, so we can write du equal to dq minus dw. Okay, so in a fuel cell, the electrochemical reactions are taking place where the reactants are converted into products in a steady flow process under isothermal conditions, right? That means what? In a fuel cell, the temperature is constant. Operating temperature is assumed to be constant. That is what isothermal condition refers to, right? So when you say isothermal condition, the temperature remains constant from the entrance to the exit of the fuel cell. Okay, and there the reactants are getting converted into product in a steady flow process, right? So what we can write is del Q minus del W equal to delta H plus delta kinetic energy. You can write in terms of D or delta, whatever it is, okay, plus delta potential energy. Let it be equation number 1, and we have what is these terms we should write, right? Where delta Q is the heat transferred to the steady state flow stream from the surrounding. Okay, that is heat transferred to the steady flow stream from the surrounding. Okay, this is delta Q, and delta W is work done by the flow stream. Flow stream means that is a reactant or product, whatever it is. Okay, stream on the surroundings. Okay, delta H is the change in enthalpy of the flow stream from the entrance to exit of the fuel cell. So remember, complete any flow stream, change in enthalpy of the flow stream from the entrance to exit of the fuel cell. Okay, and delta KE, change in kinetic energy. Delta KE is change in kinetic energy. Delta PE is change in potential energy. Okay, remember, in this system, we can say this delta change in kinetic energy and potential energy are negligible in comparison to delta W, delta H, delta W, all that. Okay, so we can say these are negligible. If these are negligible, this equation can be written as simply delta Q minus delta W is equal to delta H. Okay, these two are negligible, that is tending to 0. Okay, and if we say del Q minus del W equal to del H, you can rewrite to write del W equal to del Q minus del H. Let it be equation number 2, or you can say minus is taken outside, means you can say delta H minus delta Q as equation number 2a. Okay, and what is delta W? It is the work done, right? Work done by the flow stream on the surrounding. If this delta W has to be maximum, the process has to be irreversible or reversible. For this delta W to be maximum, the process must be reversible or irreversible. Yes, tell me. So this delta W to be maximum, the process has to be A, irreversible, be reversible? Yes, please in the comment section answer A or B. It is otherwise a type irreversible or reversible. Please type it. Type your answers as comment or in the chat box. Okay. So for this process to be maximum, delta W to be maximum, we want delta to be maximum, process should be reversible. Okay. So if the process is reversible, we have from second law of thermodynamics, we have for a reversible process, we define entropy, right? Del Q equal to T delta S. Okay, let it be equation number 3. And if you substitute this in equation number 2a, what is our equation number 2a? We have delta W equal to minus of delta T minus del Q, which is 2a. So substituting equation 3 in 2a, so what we will get is del W equal to minus of it is delta H, sorry. So delta H minus delta Q, what you will get is delta H minus T delta S. Okay. So equation number 4. So how we define this Gibbs free energy? Gibbs free energy is defined by G equal to H minus Ts, right? So we know that from thermodynamics, G is defined as H minus Ts. So if you take integral or a differential delta right in terms of delta G, it is delta H minus T delta S minus S delta T. UdV method you have to do, okay, when you take differential, right? Same thing here. UV, if you want to take differential, it is UdV plus VdU. That way we write Ts can be, you want to write in delta form, T delta S minus S delta T. Okay. So we are doing this experiment under isothermal conditions, right? The isothermal conditions, delta T is equal to 0, right? So this term is negligible. So what we have is delta G equal to delta H minus T delta S. Let it be equation number 5. Okay. So now if we substitute 5 in 4, what do you get? We can write that as maximum, right? If the process is reversible, we can say delta W can be maximum. Okay. If delta W is maximum for reversible process, right? For reversible process, when the process is reversible, delta W is delta max. So you can write delta W max equal to minus of delta H minus T delta S. Okay. And this nothing but delta H minus T delta S is nothing but delta G. Okay. Delta W max is equal to minus of delta G is what we get. That's equation number 6. Okay. Actually, we have equation number 3 where we have del Q equal to T delta S. Okay. Del Q equal to T delta S. So if you substitute that in equation number 5, what do you get? If you substitute 3 in 5 also, 3 in 5, what we get is delta G equal to delta H minus del Q. Okay. So rearranging, we can get the del Q is equal to delta H minus delta G. So now we are going to define equation, let it be 7. Okay. So the efficiency of energy conversion of fuel cell, the efficiency of, please note down these things, the efficiency of energy conversion of a fuel cell is given by delta W by minus delta H. What is that? You can say on-load voltage divided by theoretical open circuit voltage. Okay. When this efficiency will be maximum? When we have seen that when it is maximum for a reversible process. Okay. So when we have delta W max equal to minus delta G, the efficiency is efficiency maximum. Okay. The efficiency is maximum when delta W max equal to minus delta G. Okay. So what we can say is, so other way, it is V by E, voltage by on-load voltage by theoretical open circuit voltage. Okay. So that way, so this both ways we can define, this is the definition, okay, of efficiency of energy conversion of a fuel cell. So we can write eta max, I can say efficiency maximum. So delta W is minus delta G divided by minus delta H gives us the efficiency. So minus minus gets cancelled. You can say maximum efficiency of a fuel cell is given by delta G by delta H. Okay, where delta G is the change in Gibbs free energy. Okay, and that is the maximum efficiency. Okay, so with these formulas, we will be able to solve numericals where we can, if delta G and delta H values are known and number of electrons involved is known, you know what is Faraday constant. Okay, we can able to find out. Okay, because from electrochemistry we know that delta G is given by NFE of the cell. Okay, delta G equal to minus NFE, or you can say E reversible equal to minus delta G by NF. Okay, E reversible of the cell is given by this one. So you can find this E. Okay, so we'll able to know the unload voltage also. Okay, so we know E reversible value at 20 degree, 200 degrees Celsius. As the temperature increases, we should know this reversible E is decreasing. Okay, so the actual cell output voltage on the load is less than the E reversible. Okay, so the difference in the theoretical value and the actual value is called as polarization. Meaning of polarization in electrochemistry is, it is a mechanism by which there is a change in potential of an electrode during electrolysis or during fuel cell operations, because when the anode's potential becomes nobler than that of the cathode. So polarization can also be described as a kinetic deviation from equilibrium due to an electric current passing through a galvanic cell. The effect of polarization is to reduce the voltage and thereby decreasing the efficiency of the cell from its maximum efficiency. So there are different type of polarizations taking place. Okay, all these losses in the cell can be included under voltage efficiency. Okay, so that's where we are saying. So this voltage efficiency is defined as on-load voltage by theoretical open circuit voltage, which is that EMF generator. Okay. And VI characteristics, we know three zones are there. We can say VI characteristics, which we can discuss. VI characteristics. Okay, so there are three zones. Voltage regulation is poor for small values of output current and large values of output current. In practice, the operating point is fixed in the range of BC of the VI characteristic curve. What is VI characteristic curve? We'll discuss in detail. So there are three type of polarizations possible: activation polarization, resistance polarization, activation polarization, resistance polarization, and concentration polarization. Okay, so the activation polarization is about, see, remember in this reaction several things are there, right? Electrons has to move through the electric circuits, and there is raw material has to reach by mass transfer, right? Mass transfer is involved, right? All the raw material, either hydrogen, oxygen, product, water, all needs to diffuse through the gas electrode membrane, right? All that assembly, membrane electrode assembly, all that, right? So that mass transfer also coming into picture, and we know the reaction is taking place at the surface. So we have chemical reaction is taking place. Okay, and one more thing is about the electrical resistance also coming into picture, right? So due to chemical reaction, whatever is the change in the voltage, open circuit voltage, so that is called as activation activation polarization. So when what is corresponding to chemical reaction. Okay, so due to inefficiencies in the efficient chemical reaction, polarization takes place. That is activation polarization. Okay, and similarly we have, due to electrical resistances, we have resistance polarization in the voltage. Similarly, in with respect to mass transfer of the reactant, product, intermediates form, then we have concentration polarization coming to picture. Okay, so that is at zero load, that is when no fuel supply, at no fuel supply, the terminal voltage is equal to the theoretical open circuit potential. That is at zero load. We can say it as at zero load, the terminal voltage is equal to theoretical open circuit potential. Okay. As the cell is loaded, current is applied to the load voltage and efficiency drops significantly. Okay. So as the cell is loaded, the voltage and efficiency will drop significantly, and this departure of this outlet voltage from the ideal EMF is due to these three reasons, three type of polarization that is taking place. Okay. So in practice, the operating point is fixed in the range of BC. We will have three range of VI voltage range. Okay, so we'll have polarization curve. So we'll have, one is due to activation polarization, resistance polarization, and mass transfer concentration polarization. Okay, so we will try to operate in a better range. Okay, because there are three zones A, B, B, C, and C. The voltage regulation is poor for small values of output current AB and large values of output current CD. So that's why in practice, the operating point is fixed in the range of BC of the VI characteristic curve, where the voltage regulation is best, and that's where we get an output voltage around 0.6 volt to 0.6 volt to 0.8 volt. Okay, so that is the voltage we will be getting when you maintain in the range of BC. Okay. So coming to this activation polarization, So activation polarization, because this type of polarization mainly occur due to, as I told, it is only about reaction, right? So whenever there is a sluggish reaction kinetics, okay, and this sluggish reaction kinetics will depend upon, because it is activation polarization depends upon mainly the activation energy barrier. Okay, so the activation energy barrier for the electron transfer process at the electrode. Minimum activation energy is required for sufficient electron to be emitted. Minimum activation energy is required for sufficient electron to be emitted. At low current densities in the AB zone, the significant number of electrons is not emitted. So energy is supplied by output of the cell, resulting in potential loss. So this activation polarization, how we can remedial action can be taken is, we can make use of an effective electrocatalyst. Okay, effective electrocatalyst has to be used, and also we can increase the operating temperature. By these two, this activation polarization losses can be reduced. Okay, so remember this activation polarization loss is caused by, what are the causes of activation polarization? As I told, it is about reaction mechanism, what type of catalyst we are using, what type of catalyst layer morphology is there, catalyst layer morphology. So it depends upon the catalyst we are using, what is the surface morphology of the catalyst, what are the operating parameters like temperature, pressure, all that, and what are the impurities present in the system. See, if hydrogen and oxygen is used, we have less impurities. Okay, and what are the catalyst poisons involved in this, and what are the concentration of the species involved. So when I say species, it can be reactant, product, all that. Okay, and what is the age of the catalyst or the fuel cells setup, what is the service history. All these will contribute to the activation polarization losses. Okay, next in this is what taking place in the AB range. Okay, so in BC range we have some certain loss which is due to, as the name indicates, ohmic resistance or ohmic polarization. We can call it as ohmic polarization or resistance polarization. What is that? This is based upon, the resistance is based upon the conductivity, right? So it depends upon the material conductivity. In the external circuit, whatever is the copper wire are you using, or whatever wire you are using, material conductivity, material thickness. So based on this, what is the length of this thing, all that will determine this ohmic or resistance polarization. So where we have internally, we have bulk electrolyte or interface contact resistance, all that will be there. Okay, at the interface, what is that layer? Okay, so we are going to have interface contact resistance will be there. Okay, because at the electrolyte and the electrode surface, we know double layer is formed. In the double layer, what is the contact resistance is there, will be, we have to decide. That is one parameter. And in the bulk of the electrolyte, what type of this thing is there, right? So that is what inside the fuel cell, this ohmic polarization is due to the electrode electrolyte interface. Okay, and externally we will have ohmic resistance. So how to overcome this type of ohmic resistance is, what is the remedy here? The remedy for overcoming this ohmic or resistance polarization is, you can increase the operating temperature. Okay, one is increasing the operating temperature. Number two is more concentrated electrolyte is used, increasing the concentration of the electrolyte. Number three, proper shape and size of the electrode and spacing of electrolyte, so that we reduce the contact resistance. Okay, so that ways we have to placing. That's why in any electrochemical system, the gap between the anode and cathode, the electrolyte and the thing, all that will influence in this type of thing. Okay, so moving on to the another type of resistance. Third type of polarization is concentration polarization. Now, what is this concentration polarization? It is the gas side and electrode side. We are going to have limitations in the diffusion. Okay, so we can say gas phase diffusion limitation, and we are having electrolyte as a liquid, right? Sometimes liquid are in the solid phase. So electrolyte phase, it can be liquid phase or solid phase. Electrolyte phase diffusion limitation for the reactants and the products. Okay, so remember, in liquid phase, accumulation and pore blockage are the limitations. In the electrolyte, solid polymer electrolyte, even if it is solid, the blocks, we have pores through which the diffusion has to take place, but they are occupied by the foreign molecules. So thereby we have the surface blockage due to this impurity covering the surface. So instead of reactant going and occupying the surface or the block surface, that is blocked by some impurities. Okay, that will another thing. This type of gas phase diffusion will face resistance when there is accumulation of inert gases. For example, instead of oxygen, when you use air, it consists of oxygen and nitrogen. Okay, so this nitrogen is inert. Okay, so but the concentration of the nitrogen increases in the system, we are going to have buildup of these inert gases. Thereby, this gas, the volume available for diffusion of the hydrogen or oxygen is going to get reduced, right? So this will contribute to the concentration polarization. And how to overcome this type of concentration polarization is, we have to use, we can increase the temperature for gas side polarization. Okay, so gas side concentration polarization. So increasing the temperature will increase the movement of the gas molecules. We know that. So increasing the operating. Remember, all type of polarization, one of the factor, one of the remediation is increasing the operating temperature, right? So here also increasing the operating temperature. Whereas for electrode side, you can increase stirring or circulating the electrolyte. Okay, so if it is liquid electrolyte, we can introduce stirring or circulation of that. Okay, stirring or circulation of the electrolyte. So that will help us to overcome the concentration polarization. So apart from these three type of polarizations, we have other polarization losses, which is one is electrical short circuit in the fuel cell. Another thing is crossover of the reactor. It is one of the important problem that we face. We are going to discuss in detail also. So we also always talk about hydrogen and oxygen, right? Hydrogen does not goes to the other side. That is one of the primary duty of the electrolyte. It should not allow the reactant to pass through it. Okay. So even if it is a polymer electrolyte, polymer membrane electrolyte, one of the duty is it should not allow the reactants or any intermediates or products formed to pass through it, right? Because if it goes there, there is some other reaction will take place. Okay. So this crossover of reactants or even the products through the electrolyte and subsequent mixed potential reaction that may take place at the opposite electrode or other electrode. Okay, so because of that also we are going to have other type of polarization. Okay, so these are the various things we have to understand. Okay, so that is what about VI characteristics of a fuel cell. Okay, we should know this activation polarization of the hydrogen oxygen reaction is much smaller than the activation polarization of oxygen reduction. Okay, I'll just summarize what we have discussed so far. So in this lecture, we have discussed about what is Gibbs free energy, what is the heat of formation of pure elements, all that. I have seen the what is the reaction taking place at the anode and cathode when you are using acid electrolytes, and what is the reaction taking place at the anode and cathode when you use alkaline electrolytes. Okay, so the reaction taking place at anode is, however, HOR, that is hydrogen oxidation reaction. The reaction taking place at the cathode is ORR, which is oxygen reduction reaction. Okay, so we know that in case of acid electrolyte, it is the H plus ions moving from anode side to cathode side, whereas for alkaline electrolyte, it is the anions which is moving from the cathode side to anode side. Okay, so we have discussed about the conservation of charge, and we have seen what is first law of thermodynamics, and for any work done to be maximum, it has to be a reversible process, and we have seen what is the energy, what is the constituents of energy. Okay, so we have written the what is the heat transfer to the steady flow stream, work done, change in enthalpy, all that. And in this, we have assumed the change in kinetic energy and potential energy are negligible in comparison to the other parameters. And we seen that it has to be reversible. So we got delta W maximum is equal to minus delta G. So we define the efficiency of the energy conversion of a fuel cell given by delta W by minus delta H. So delta W is equal to minus delta G. So we get a maximum efficiency as delta G by delta H. Okay. So if you are able to calculate delta G and delta G and delta H, we will able to solve the numerical and get efficiency of a fuel cell. Okay. And from electrochemistry also we know that delta G equal to NFE, where so you can rewrite to get E equal to delta G by NF. So once you know delta G and once you know number of electrons involved and Faraday constant, you will get what is the EMF generated in a fuel cell. Okay. And we have seen what are the three type of polarization majorly taking place in case of a fuel cell: open circuit potential when the load is on. Okay. So that is discussed in this lecture. And we know that how to calculate the delta G values and delta HF values. Okay, so in delta S value, how to determine as a function of temperature. All these things we have studied in your UG courses like the chemical process calculation. So all that you can brush up, refresh things. Okay, so these are some of the values for HF value and S value. If you want to solve numericals, we'll make use of these values. Okay. Heat of formation and entropy values for water in liquid phase, water in vapor phase, hydrogen and oxygen. What is HF value? We know it is 0. What is the entropy value is given here. Okay, so this data will make use when we solve the numericals. Okay, also we know how to calculate MCP delta T, all that, right? So to get CP value as a function of temperature when it is for different, if it is for H2, what is the CP value, for water what is the CP value, and hydrogen what is the oxygen what is the CP value is an expression given. So if you know the operating temperature, CP value can be determined using these expressions. Okay, and if you look at the plot, this plot we have, so the Gibbs free energy change at various temperature can be seen for steam, for liquid. Okay, how it is changing. Okay, so what this graph is showing us, It's somewhat obviously that the energy obtainable from a fuel cell reaction will decrease with the temperature at which the reaction is carried out. So this, however, is not the only reason for the lack of efficiency at high temperature, as we are going to discuss in detail with each type of fuel cell. Okay, so we have a data where the temperature of these operating temperature is increased from 25 degree to 100,000 degrees Celsius, and you can see the delta GF value, Gibbs free energy change, which is decreasing. Okay, which means that delta G is decreasing. What happens to the efficiency? Efficiency is, numerator is delta G. If the numerator is decreasing here, you can see here delta G is in the numerator. If delta G is decreasing, obviously the efficiency will decrease. So as we are increasing the temperature, and the temperature is increasing, delta G is obviously decreasing, therefore efficiency is decreasing. So when you increase the operating temperature of the fuel cell, the maximum obtainable efficiency will be decreasing. Okay, so that's what we can see from that one. Okay, so we have seen about this irreversibility. If there were no losses, if the fuel cell process is operated completely reversibly, what we are supposed to get? We are supposed to get 100% conversion, right? We should get 100% efficiency into that. What is that 100% efficient mean? This Gibbs free energy should be converted into useful electrical energy. But however, losses or irreversibilities creep into the every system. For example, some of the energy released in the reaction will inevitably leave the system as heat. So once it has floated away in a warmer air, that energy cannot be recovered and turned back into useful electrical energy. That's why we call it as irreversibility rather than a loss. Okay. So but if you consider the heat engine, no, in that case we consider it to be loss. Loss is coming into picture because Carnot limitation is there, T1 minus T2 by T1. Where T1 is the maximum temperature of the engine and T2 represent the temperature of the exhaust, all in kelvins. So the limit stems for the fact that there is always going to be some energy proportional to T2 which is lost. And we know that these fuel cell systems are not seconded to this limit. So how do we give a measure of their efficiency? We have already seen that it is a Gibbs free energy that is converted into electrical energy. If not for irreversibilities, all of this could be converted to electrical energy, giving a 100% maximum efficiency. We could therefore define the efficiency of the fuel system as electrical energy output by Gibbs free energy change. And this is the case, however, no matter what the reaction conditions are, the efficiency limit is 100%. Therefore, the figure is not really much use to anybody. A common measure of the energy contained in a fuel is its calorific value. What is calorific value? It is a measure of the heat that would be produced by burning the fuel. A more precise measurement is the change in the enthalpy of formation, delta HF, as with the Gibbs energy. The convention is that a negative value translates to more energy released during the reaction. Using this value, we can able to obtain more useful efficiency value of the fuel cell. So efficiency value of a fuel cell is electrical energy output per mole of the fuel by delta HF. Okay. So recall, however, that the delta HF of the steam is different from that of liquid water. Hence, there are two possible efficiency values for a given process depending upon the phase in which the water is leaving the system. If you refer to the table below, we have delta HF value for this hydrogen plus oxygen forming water. Depends upon the product. If water is in liquid form, we have a value, higher value. When water is in liquid form, we have a lower value. Okay. So that's what we will able to find out. Okay, so we can refer to as higher heating value and lower heating value. Okay, so we can express the maximum possible efficiency as delta GF by delta HF into 100%, which is often termed as thermodynamic efficiency of the fuel cell. So we can use this equation along with the other equation to get the maximum reversible EMF values also. Okay, so if you look at this image, we have efficiency versus temperature. The efficiency is decreasing with the increase in temperature for fuel cell, whereas if we consider this Carnot, it is increasing. Okay, Well, in this lecture number 7, we have derived an expression for efficiency of a fuel cell. So where we have discussed about the thermodynamics of fuel cells. In the next lecture, we will solve few numericals to determine the efficiency of fuel cells or the voltage developed by a fuel cell. Then we are going to discuss about classification of high temperature fuel cells or particularly high temperature PEM fuel cells. Thank you so much for joining my classroom. Meet you in the next lecture. Bye bye.